I'm just going to give you now an even quicker overview of a project that we're starting here, mostly in the CS department, but with partners from different places around campus. Josh's talk was a great introduction. I think looks like Josh took off. Oh no, he's in the back. So Josh's talk had embedded in it exactly the vision we have, which is looking at how do you build systems that combine these three elements, algorithms, machines, and people, to solve data-intensive problems. So, basically, the sort of the industry buzzword for the problem we're addressing is, the big data problem. And so there's lots of ways to think about big data, but, web companies of various sizes, are dealing just with massive amounts of data on a daily basis. So, Facebook, is looking at hundreds of terabytes a day in new log information. They're managing 20 petabytes of user information in various ways. Google is, as you can imagine, processing huge amounts of data every day to basically run their entire business and improve their service. Science is generating even more data than that. And, you can look all over the place to find big numbers about the amount of data that people are dealing with. So there's no real surprise there. And, this is just growing as there's more and more devices. People are getting more and more connected. And, storage continues to get cheaper and cheaper. And so there are people making arguments now that it's actually cheaper to just keep all the data rather than to spend the effort to figure out what to keep and what to throw away. Any of us who own garages or attics already knew that, right? So, the interesting thing, though, is this isn't just, you don't just have to be CERN or Google or Facebook to have this problem. All sorts of places are having this problem. And so, it's really just this issue of, are you really sure you want to delete that? Do you really, and so, the issue isn't so much the number of bytes you're dealing with, but it's really, this stuff here, which is, there's more and more sources, the data's of different types, it's not curated, so it's hard to, understand things about quality, it's not mutually consistent, and, there's sort of this traditional data integration problem. I mean, Laurent mentioned in his talk, just getting the data and getting it into a format that you can do anything with it is really a huge part of the challenge. And so what we're doing in the AMP lab is really trying to get a handle on this big data problem. And so the first thing we did was to try to come up with a definition of big data, one that would scale over time rather than picking sort of a certain amount of data that you have to be considered to having a big data problem, and if you have less than that, you don't. And really what we hit on is that there's really two key things that you have to worry about. If you're trying to make a decision based on a lot of information, you need to be able to make that decision within a certain time frame. So you need a timely answer, and the answer you get has to be of sufficient quality so that you can make your decision with some amount of confidence. Okay? And so that's really the yin and the yang of data analysis. You want the answer fast enough and you want it good enough. Okay? And if you're having trouble getting one or both of those for your particular problem, then you effectively have a big data analytics problem. So, as the name of the lab implies, we really feel that there are three things three types of resources we're going to have to integrate in order to solve the set of problems that we think need to be solved. And, on the algorithm side, it's about scalability, it's about efficiency, and it's about answer quality. And being able to adapt and adjust those various things. On the machine side, we're looking at warehouse scale computing and how do you scale up data centers. And on the people side, as we just saw in the previous talk, there's tremendous advantages to be gained by figuring out where exactly in your analytics pipeline the people need to be. Because if you put them in the right place, they're going to solve your problem, dramatically, much better than, any, large number crunching machine can do. If you put them in the wrong place, they're going to slow everything down and they're going to get the answers wrong. Okay, so there's a huge design challenge in figuring out where in the processing and where in your system you want people to be. Okay, and that's really what we're doing in the lab. And so a nice way to think about it is really along these three dimensions. And if you look at existing data-intensive systems, they tend to fall along one of these three dimensions. And so data management systems like Oracle or analytics platforms like Hadoop and MapReduce, those tend to be very machine-oriented. So the game there is, can you run on more and more machines? Can you leverage more memory and disks and so on? Along the people axis, there are all sorts of different crowdsourcing types of platforms. We just show two of them here. Amazon Mechanical Turk, which I'll talk about a little bit more in a second, is a marketplace for people who are willing to do work online and the people who are willing to pay them to do that work. Yelp is a different kind of crowdsourcing system where it's user-generated content, and so people contribute to that because for a whole variety of reasons. One is they like the recognition. Two is they enjoy being part of that conversation. Three is they like to help people, and so on. Okay, and so there's a bunch of systems that are really emphasizing the people side. On the algorithm side, there are more and more tools for making sense of data and doing richer and richer analyses. So we just show sort of MATLAB and R as examples for these things. And, systems that sort of start moving into having multiple dimensions. So, we look at like web search. Well, that's heavily machine-oriented. It's, massively parallel. There's a lot of algorithms going on, and there's some people involvement. There's some human involvement in tuning results and things like that as well. And then more recent things like IBM Watson, maybe fewer machines. It ran on dozens of machines rather than tens of thousands of machines. Probably more sophisticated algorithms in a lot of ways, and more involvement of people. Okay, but even so. We think that there's really a tremendous opportunity to sort of be able to be at the right spot in that three-dimensional space. And so, the way we think about the AMP Lab is, being somewhere in the combination of these areas so that for a given problem at a given time, you could use the right combination of resources. And that's really what we're doing. So, structurally, we've set this up as a 5-year project, and our goal is to develop a new generation of data analysis methods, tools, and infrastructure for making sense of the world at scale. Okay, that's kind of our mission statement. And just to give you a feel for who's involved and how we're organized. So these are the main set of faculty that are involved right now. We're actually all housed in the CS department, except for Alex Bayan, who's comes from civil engineering department, but works very closely with people in EECS. And what you can see here is we have a pretty wide range of specialties within computer science, right? So it's still a computer science group, but we've got systems, we've got networking, we've got databases, we've got privacy and security, we've got machine learning, and so on. Okay, and if you haven't seen it yet, what we've done is we've reconfigured part of Soda Hall. This was something actually that was done for a previous project where we turned it into a big open collaborative space, and the majority of these faculty actually sit there in this open space with the students and the postdocs. So we've basically given up our regular offices to sit in this shared space so that we can all work together. And so it's a highly collaborative environment. And the other thing that's interesting about the lab is it's primarily industry funded right now. And so Google and SAP put in major donations to get the lab going. And we have a bunch of other companies who've also are supporting the lab very generously. And we meet regularly with these guys. We have every 6 months we have an offsite retreat meeting. Students present their work. Visitors from the companies critique it. They give suggestions. They kind of steer us away from dead ends. They point us at problems that maybe we didn't realize existed, and so on. And so a big part of the lab really is this nature, this collaborative nature, both across sub areas of computer science and between academia and industry. And that's one of the reasons why I think it's really an exciting opportunity for doing research. in order to build systems that actually solve problems and to sort of help us focus on the right things to be, the right problems to be solving, we looked around campus to find people who had problems that fit into basically the big data analytics umbrella. And so here are a few people that we're working with. One is Alex, who I already mentioned, who runs the Mobile Millennium Project on large-scale crowdsourced sensing, originally for traffic, but now for all sorts of environmental sensing applications. Paul Waddell over in the College of Environmental Design does very detailed urban microsimulations based on existing data, existing laws, and then simulations of what's going to happen as you change things in the environment. Ken Goldberg, in the Center of New Media, has a group that's built a tool called Opinion Space, which gathers, it's an online forum for people to express opinions, find people who have similar opinions, comment on the opinions of others, and so on. And they've had a couple high-level or high-profile deployments. One is at the U.S. State Department. If you go to the State Department's webpage, you'll find their system running. And then a number of companies, General Motors being one of them, have started using this tool to try to understand at a broad scale, what are people thinking about in the world about their particular set of issues. And we're in the process of starting a collaboration with a group over at UCSF that's doing sort of personalized medicine, taking kind of high throughput gene sequencing, mixing that with clinical data and other information in order to tailor medical recommendations and treatments. And so, one thing you'll notice about these collaborators is that they're all in the academic space, which we believe means it's going to be easier to share data and to let us get access to their data. There are also people who already have problems that they're trying to solve, and so they're highly motivated to working with us. And so I think that's a big part of the project as well. So what I want to do quickly, and I realize I started late because of the technological snafu here, so I'll probably won't get through all of this, but let me just tell you what we're doing research-wise. So, again, the idea of big data isn't just number of bytes. It's really these issues here. It's the diversity of the data. It's the fact that you never see all the data. So I'm a database person by training. When you run a database, I'm about to run out of here and go teach my introduction to database class. When I do that, I'm going to tell the students, you have a database, it's got a bunch of information in it, you run the query, and then the query gives you the answer based on all the data that's in the database, right? That's the rule. That's not true in this world, right? You never see all the data. So you have to think about how do you selectively look at information, how do you go out and get the information that you don't have, that you need, and so on. How do you do sampling and things like that. And then as you scale up, if you look at enough information, you basically see everything, right? And so how do you tell what's real from what's sort of just an artifact of the fact that you're looking at so much data that you start seeing all sorts of correlations, some that may be there, some that might not be there. All of this factors into this bullet here, which is basically just saying the goal is we want to give people the ability to get reliable answers from data that's fundamentally unreliable. Okay, so we're going to have to be looking at algorithms that return indications of their confidence, of statistical significance. There's a part of the project that's looking at putting error bars on answers and then allowing users to help steer the computation to change, to sort of reduce the error bars where necessary and so on. In order to make all this work at scale, we do have to build out the infrastructure, and so we've got projects that are working on an operating system for the data center. It's a system called Mesos, which basically allows users to run lots of different computational frameworks together. So if you do Hadoop, MPI, other types of computation frameworks and operating systems, you can get all that stuff to work together, and you can share resources across them so that you can make effective use of the resources you have. We're doing work on kind of higher level interfaces to cluster computers, and so we have a project called Spark, which is basically a high-level language for expressing machine learning algorithms and other types of iterative computations that can be much more efficient than sort of the standard Hadoop-based approaches, and so on. And then, again, this other issue that I mentioned of the fact that through systems like Mechanical Turk, where you have access to people out on the internet who are willing to do work, and through more specialized types of systems like the one that Josh talked about, where you have access to people who have expertise in certain areas, you can bring people into the analysis process really at any point. Okay, and so the way we tend to look at this is that, in some sense, people are part of the problem, right? Because a lot of the data we get, especially if you look at the text, and things like Laurent was talking about doing analysis of, and other places you get data from people. So, people are part of the problem because they're providing the data, and that data is messy. They're part of the problem because they're the ones that are asking the questions, and sometimes they don't actually know exactly what they're looking for. But they can also be part of the solution because people are really good at certain things that computers aren't. Pattern recognition of certain types, outlier detection, making sort of subjective comparisons, going out and finding information that isn't readily available. Those are all things you can ask people to do for you. And so we're looking at how to leverage those types of capabilities as well. One thing we know for sure is that because of really all these things, the fact that you can never see all the data, the fact that you have people that are consuming the results of the analytics, and so on, we want to run the system in a mode where it doesn't. You don't ask a question and it gives you an answer and stops, but you ask a question and it starts giving you answers with certain quality and can continually improve those answers. By getting more data, by running different algorithms, by asking people in the crowd, and so on. Okay, and so it's a sort of pay-as-you-go continuous improvement model. And finally, since we envision a system where you've got lots of computational resources, you've got lots of people resources, we haven't talked really so far about mobility and things like that, but you've got a lot of resources out in the environment. How do you manage those resources effectively and efficiently and in a fair way when you have lots of people trying to use them? So I had actually a bunch of details on some specific projects we're doing, but I think if that clock is correct, I think that's the end of my time slot. So I apologize for the abbreviated introduction. But if you're interested in finding out more about what we're doing, just let me know or let Masoud know, and we'll tell you more about it.
Thank you so much. Time for few questions. So what about this spam? So because you said that people represent themselves not as they are, and you start looking at this information, how do you actually, because like a search, when you look at the websites, so the websites that they are not representing themselves correctly, right? In a lot of cases. So you have the simple algorithm of the Google, but that doesn't work if you start going to the real world because of all these spam and everything around it. So how do you deal with this concept in the AMP lab?
Yeah, so when you get people in the loop, tempted to show one slide. Let me show one more slide. Then I will. Let me just. Sorry, I wasn't actually going to show all these anyway, but this might help a little bit. So if you look at integrating people into the processing, there's a bunch of dimensions that you have to consider, and one of the issues is sort of in terms of reliability, right? So when you're trying to do computations over lots and lots of machines, especially commodity ones, you have to build systems and algorithms that can tolerate continuous failure of parts of the system. Okay, when you deal with people, you have those issues, plus you have the problem that they might be trying to be malicious. And so there's depending on the problem you're trying to solve, there are a bunch of different techniques that people use. So certainly you want to ask multiple people the same question and compare answers. You want to do statistical analysis of individual answers to individual questions, plus you want to watch people over time and understand their behaviors to see if you can figure out, who's trying to help you and who's trying to hurt you. And then there are a lot of mechanisms that people have already built. If you look at, say, some of the opinions-based stuff that Ken Goldberg did, where, people establish reputations. There's kind of the community is kind of self-policing in a way, and you learn over time, sort of who's trustable and who isn't. And there really isn't a perfect answer. There's not a nice, when you move sort of from the cloud point of view, where there's plenty of technical challenges, to the crowd point of view, you sort of have all those scale problems, plus you've got, all sorts of problems that happen just because you're working with people. And that's part of the real challenge and the fun of what we're doing, I think.
Just maybe one quick follow-up question. Yeah. So what about the science part? Because I look at more, these are the sense of the business aspects people they do. Now if you go to the science, which is real completely different domain, and they have large scale and is exploring like what the Josh says or others. So how do you deal with that?
So it's interesting. So when we started the project and we knew that we needed to get applications on board early, we decided that we would try to find applications that were a little closer to the business side, because we felt that those would be harder to find in a way, because we all know, and all the people on the list, all work with people in the sciences, and we already understand that they have lots of data and probably more data than a lot of the applications that we're looking at. And so our view was to start with these applications, see if that leads us in an interesting way, and then start bringing in some of the scientific applications. That's why we're starting this new effort with UCSF. And we're interested in talking to other people on campus. That's why I came to present here today. So,
great. Thank you so much.
Okay.
And the last panelist, so Ram Akela, that is a professor at the computer science at the UC Santa Cruz, and also he's visiting faculty at CITRIS. So he will be presenting larger scale inference in computational marketing.